one. There's also the video. That's the video that I did from Monday, and I'll be uploading today's video also. But the slides that we're going to be covering are right there. And then, of course, there's the homework and the quiz that you need to be working on this week. All right, so I have to share the window here. I think I'm just going to share my entire screen so I don't forget if I have to flip over to another screen. Okay. All right, so the first set of slides we're going to work on here, talk about voltage and current for the most part, also a little bit of resistance, but electricity comes from atoms, all right? So atoms, of course, make up everything. You know, they make up us, they make up these computers, they make up, you know, the rain coming down right now. All of that is the basic building block is the atom, all right? And so atoms have a nucleus, and inside of that nucleus is what they call protons, which are positively charged particles, and also something called neutrons. A neutron is made up of a proton and an electron fused together. So neutrons do not have an electrical charge. Protons have a positive charge, and electrons have negative charge. And the electrons actually orbit around the nucleus, kind of like our solar system, where the Earth and the other planets orbit around the sun. All right, and so that's kind of, this is basically Bohr's atomic model. So this is the ideal model that a scientist Bohr came up with. Okay, but it really helps us understand how various molecules come to be, and also how electricity works, and why certain materials are good at conducting electricity, and other materials are very bad at conducting electricity. So something that's very good at conducting electricity we call a conductor. Something very bad at conducting electricity we call an insulator. And so if we look at the periodic table of elements, so inside of this, every one of these elements is an atom, okay, or, you know, a group of atoms, right? And so over here on the left, on the far left, we see there's hydrogen, and then lithium, and several of these, all these are in the yellow, lithium and sodium and stuff are considered alkali metals, okay, which means that they're very, very, very reactive, right? And then over on the far right, we have what they call inert elements, which are actually all gases, okay, because they don't react with anything else, even themselves, because they have the perfect match of electrons. And so we have like helium and neon and argon. These are gases, and because they don't like to react with anything, okay? So, and then over here in the middle, we have like at number 6 and 14, we have carbon and silicon. Carbon and silicon are what we call semiconductors, because they're halfway, even though in this periodic table it doesn't look like they're halfway, but they're actually, as far as their electron bands, we'll talk about it in a minute, they're halfway between being really, really happy, like these gases on the far right, and being kind of very reactive as the metals on the left. Okay, so what we have here is just this lays it out. So we have very reactive metals on the left, semiconductors kind of in the center, and then the what they refer to a lot of times as the noble gases on the far right. All right, so that slide pretty much explains everything I just talked about, except for the one thing down at the bottom. We see a coulomb. A coulomb is a count of how many electrons that we need to make up 1 amp, and we'll see that a little bit later there. But a coulomb is kind of a when you look at the atomic numbers on here, so you see like well, 6 is the atomic number, but there's also an atomic weight. I guess it's not shown on this version of the table of elements, but some table of elements will also show you the atomic weight of these, like, you know, how much does carbon weigh or how much does silicon weigh. And when you look at that atomic weight, it's based on a coulomb, which is 6.24 times 10 to the 18, okay, elements within there, or individual atoms, okay? And so when we're talking about current, we talk about 1 amp per second. 1 amp per second would say that we have at one point in circuit 6.28 times 10 to the 18. Okay, that's an awful lot of zeros there. All right, so let me flip over to paint here for a minute, and let's put those zeros in there. So we've got 6, okay, 6.24, okay, and then okay, so that's what do I got here? There's 9. Okay, so I need another 9. Okay, so that is how many electrons are going to pass a point if we have 1 amp of current. Okay, that's an awful lot of electrons. Okay, that should actually be a comma the way I wrote it there instead of the period. Okay, but so that's a really, really, really big number that we see there. All right, so when we're working with electricity, okay, we basically are talking about energy, right? We're talking about moving electrons. So these moving electrons, okay, they're energetic, they're moving. So what makes them move? Well, we need a force to move. So force is measured in newtons, okay? And when we talk about electrical force, we're basically talking that you have protons that have a positive charge and electrons that have a negative, and those two opposing charges attract each other. And so it's that attraction, which is that force, which causes the electrons to move, okay? And work is a measurement about how much how much energy is either moved, or if we're trying to store it, how much is being stored. But work is how much you're actually doing. So if you say, okay, I'm going to come and push on this wall. Okay, so I've got this wall behind me and I'm going to push on it. All right, and I can push here and I can sit here and push all day until I'm totally exhausted. But if I don't move the wall, I haven't done any work. Okay, so force is defined as, work is defined as force times distance. Okay? And so it's how much did you actually make something move. And so that's the definition of work. Okay. All right. So when we talk about the movement of these electrons, that's basically the definition of current. Current is the movement of electrons. Okay. So if we have here a battery, so these are like battery terminals at the left and right here. So at the right, we have a positive battery terminal, which has a big positive charge. And at the left, we have the negative battery terminal where the electrons are stored. And now if we put a conductor on these two terminals, we're going to get electron flow. So, and I said this Monday, electrons through solid materials, the electrons are really, really small. Protons are much, much, much larger than electrons, and the protons are actually grouped together inside of that nucleus. So if a proton's going to move, you got to actually move that whole nucleus. And then if that nucleus is like carbon, it's got 6 of those protons in it. And so that means you got 6 of these great big things all bundled together and you're trying to move them. So inside of solids, protons or positive charges really don't move. So when we talk about electricity through any kind of solid material, you're talking about the only thing that's really moving is the electrons. The electrons are extremely small and they can fairly easily move. And so through any kind of solid material, it's the electrons that are really moving. Okay. And so what we actually get is the electrons are going to leave like the negative terminal of the battery and move through the conductor, and then they're going to meet up with a positive charge at the positive terminal of the battery. And then when that electron meets with that proton or that positively charged atom, what happens then is the balance now is balanced out. And so that's why like a battery will go dead, is because all the electrons have joined with their positively charged atoms, and now there's no charge there, so there's no difference. Okay, so basically when you charge a battery, what you're doing is you're separating those electrons and collecting those electrons over at the negative terminal of the battery, which is, so you're kind of stripping those off of the positive terminal and taking those electrons and moving them to the negative electrons. That's effectively what you do when you're going to charge a battery. All right, so mathematically, current, we use the symbol I for current. So I actually, it comes from the French word intensity, because the French scientist who did a lot of work in this area thought, hey, if I get electrocuted, that's pretty intense, right? So, kind of the idea of it anyhow is the fact that he said that the current is intense. So he used the symbol I for intensity. And Q, well, you see there, Q is the charge, okay? And then T is, lowercase t is time. So current mathematically is defined as the amount of charge that passes a point in a given amount of time, specifically in 1 second. All right. So again, I is for the intensity of the current. Okay. And the unit of charge is in coulombs. So remember coulombs, that was that number I had over here, right? 1 coulomb is 6.24 times 10 to the 18th. So that's 1 coulomb is this many electrons. Okay. So 1 coulomb is this many electrons. And so what we're saying with this current is if that many electrons, if this many electrons move past a point, okay, so let me draw a line here. All right, so if we say this many electrons move past this line in 1 second, that is defined as 1 amp of current. Okay, so that's defined as 1 amp of current. That many electrons moving past that 1 point in space in 1 second. That is the definition of 1 ampere of current. Okay, a lot of times I kind of abbreviate and I say amp, but technically the correct unit is ampere. Okay, so we use a capital A to represent the unit ampere. A capital C represents the unit coulomb. Now, why do we use a capital A and a capital C? Because these units are named after a scientist. Okay, so it's a proper noun, it's named after a scientist. When we talk about like seconds, seconds of course is a measure of time, you use a lowercase s because it's just a unit of time, but it's not named after a scientist. Okay. All right. When we talk about AC and DC circuits, technically this class is DC or direct current. What that means is that the current is only moving in one direction. AC refers to alternating current, which means that the current moves to the left and then it moves back to the right. Okay, and so AC refers to alternating current, where it's alternating. Half the time it's going left to right, and the other half it's going right to left. Okay, so the if you're talking about current, capital I indicates the current for DC current, and a lowercase I, when we get to AC next semester, we'll be using lowercase I to indicate alternating current. And you can actually have both DC and AC currents in the same circuit. All right, now current is the flow of these electrons, and however many current electrons you have flowing into a given device, like a battery or a light bulb or a transistor or a resistor, okay, if you have 6,000 electrons going in, you're going to have 6,000 electrons coming out the other side. Okay, so current is the flow of those electrons, and so and those electrons are flowing the same everywhere in the circuit. So let's flip back. On Monday I kind of showed you, I had this one drawing in here under week 1. Right, I had this circuit here, and I had this circuit here in week 1, or on day 1. We kind of talked about this, and so we have these electrons are flowing through here, and so when you have electricity, okay, the electrons are moving through, and basically what's happening when you close the switch and you get this electron flow, these electrons, as they start moving, they push the electrons, they're pushing the electrons further away from them. So if you think about like a train going down the track, right, you have the engine pulls a car, and then that car is attached to another car behind it, which is attached to another car behind it, and so they're all moving. So when that engine starts moving, all the cars connected to it, right, the entire train starts moving. Now there is a little bit of slack, right, in there, so you get a kind of little bit of stretching as it starts to move. But for the most part, once that train starts to move, the entire train is moving. Okay, and that's the exact same thing with electricity. Once you close that switch, the electrons the electrons near the battery start moving. But when they start moving, they all start pushing the electrons in front of them. Because they need room. If this particular electron down here at the bottom is moving, and it's gotta have room to move, and so it's effectively going to push the electrons next to it. All right. So these electrons coming out the bottom of this battery, they might not actually move very far. Okay, they may never make it all the way around the circuit and into the top of the battery. But what they're doing is they're pushing the electrons in front of them and pushing the electrons in front of them and pushing the electrons in front of them. So, when you get, 6,000 electrons coming out of the bottom of this battery, you also have 6,000 electrons being pushed into the top of the battery. Okay? So like I say, the electrons actually coming out, they may never actually make it all the way back around through the battery, but the same amount of electrons that came out of the bottom of the battery are going to go into the top. Not the same electrons, but the same number of electrons. All right, so current in is always equal to current out. Okay. Current, not voltage, is what actually causes damage that can cause your heart to stop. Okay, so when you get electrocuted, you hear people say, well, 500 volts is enough to hurt you or possibly kill you. It's not really the voltage that is going to do the damage. What the damage is done by those electrons flowing through your body, and especially through your heart muscle, right? So all your muscles in your body are actually triggered by electrical impulses. So when you want to open or close your hand and you're using those muscles, your brain is sending electrical impulses to your muscles, telling it which muscles to open or close. And so it's those electrical impulses, when you get current, you get these electrons flowing through your body that aren't coming from your brain, they send confusing signals to your muscles, and that's actually what is dangerous to you. So that's you get, number one, you get too many electrons, all right, coming through, and if they go through your heart, then they could cause your heart to not work properly. And so it's the current that actually does the damage. So here's a little table that gives an idea of how much current in milliamps. Notice this is milliamps, so that we're talking 1,000 less than 1 amp. Okay, and so you see here with just 1 milliamp, you're going to you can feel that on your hand. Okay, but if you get up here around 100 milliamps, then it's going to be very painful, and it could cause breathing or other muscular control issues, which, like I say, your heart is a muscle, and it can affect your heart. All right, so this is just kind of a sketch here showing this imaginary plane. When you're trying to measure current, You can measure it at any point within the circuit, inside of the battery, inside of the light bulb, or inside of any of the wire. And what you're counting when you're trying to measure electrons, you're calculating how many of those electrons are moving past this imaginary plane. All right, so let me just flip back here, see if anybody posted any questions. Okay, I don't see any questions at the moment. All right, so voltage, okay, is defined as work divided by charge. All right, and so mathematically we use V for voltage, W for work, and Q, I already mentioned, is how much charge you have. So voltage is basically kind of saying how much work can you do. Okay, so your voltage is work divided by the amount of charge that you have available. Okay. So that's kind of the definition. So notice here, when we look at voltage, it's defined based on the work and the amount of charge. Work is actually measured in a Newton meter, because remember, work is force times distance. So a Newton is the amount of force, and distance, meter is a distance. And so work is the unit of measurement of work is a joule. That joule is a defined unit based on the Newton and the meter. And I kind of mentioned this on Monday, but voltage, we also use some terms of, we can sometimes talk about being potential difference. It's a difference between the positive charge and the negative charge. If something doesn't have a separation of charge, then it's neutral charge, there's no voltage there. All right, so the voltage, we a lot of times when we talk about measuring voltage, we talk about like a voltage drop. That's because we have a high potential on one side and a lower potential on the other. And so we talk about as you go through this device, as current flows through this device, you get a drop in voltage. Okay, so I'll use the term voltage drop a lot when we talk about this resistor is dropping this much voltage. Okay, but really we're just talking about what is the voltage across that element in the circuit. Okay, now if we think about trying to like do an analogy, because we can't see voltage, so sometimes it's kind of hard for us to understand voltage and current, because we can't see the electrons moving, we can't see the voltage. Okay, but if you think about water, okay, like water pressure in a hose, then we can draw analogies between water flowing through a hose and voltage and current. Okay, so the voltage is like the pressure that pushes that water. Okay, voltage is the pressure that's going to push it, and the actual flow of the water is the current. All right, now to understand the difference between a conductor and an insulator, we have to kind of go back to the model of the atom. Okay, and so the Bohr's model of the atom, as I said before, we have the proton, and the proton, all the positive protons are positively charged, and all those positively charged protons are in the center of this atom, so they don't really move. And there's also might be some neutrons in there. Okay. Now, outside of that, the electrons orbit around the nucleus. But the electrons also have what they refer to as energy bands. And so there's multiple different energy bands. The first energy band, the one closest to the nucleus, only accepts 2 electrons. Okay? So it only accepts 2 electrons in this energy band. Once it gets those 2, it's happy and it won't accept any more. All right? So when we talk about like helium, helium is a noble gas, and it's got 2 protons. And so when it's got 2 protons, and then it's got 2 electrons orbiting it in that band, it's happy. It's got the perfect amount for, it's got 2 protons, it's got 2 electrons, it's got a neutral charge, and this energy band, it only wants 2 electrons, so it's happy. And so we end up with helium. And as everybody knows, right, helium is a gas. And if you put the helium, a whole bunch of helium in a balloon, it's going to float up because it's a gas and it's light and it's not going to react. Okay. Hydrogen is also a gas, but hydrogen is actually very flammable because hydrogen only has 1 electron, okay, and 1 proton. So an uncharged hydrogen is missing in this valence band here, or energy band. It's missing 1 electron, and so it's actually willing to react with some other element because they want to make this band full. Okay. So there's 2 things going on here. The one, we got a positive and negative charges going on, but then we also have these valence bands, and they like to be full. And if they're not full, then we get into these different types of materials. So in this case, what we're looking at here is copper. And copper has 29 protons. And so if there's no electrical charge on it, it'll have 29 electrons. Okay? But when you look, the inner band will only accept 2 electrons. The next band out will only accept 8 electrons. The third one will accept 18 electrons, but that only gives us 28 electrons. And so if we don't have a positive or negative charge on this atom, then it needs 29 electrons. But that 29th electron is out here in this 4th band all by itself, and it's lonely. Okay? It's lonely out here in this band. And so it would actually be happier in a way if it got rid of that electron. If we knock this electron off of here, then the atom says, hey, I've only got 3 bands, but they're all full, and that's good. Okay, so we would actually have a positive charge now because we're missing 1 electron. We got 29 protons, but only 28 electrons, so we have a positive, overall positive charge of 1. But our band is, all the bands that we have are full. And so we've got this 4th that we can just knock that other electron off, and we're still kind of happy because the bands that we have are all perfectly full. And so this other electron is just out here by himself, and it's like, yeah, just go away, which is maybe kind of rude, but that's kind of what it is. So when we talk about conductors, the best conductors have 1 free electron in their outermost band, and all the other bands are full. So we have just this 1 spare electron in the outer band. It's not allowed in any of the inner bands because they're already full up in their spots. Okay? And so that's what makes the best conductor. So when we look at this periodic table again, okay, you see your bands. So if you look at the first two elements are hydrogen and helium up here at the top. And see, they meet that innermost band with just 2 electrons. So you can either have helium, which would have a hole here, or excuse me, a hydrogen, which would if it had a neutral charge, meaning I have a positive, I have a proton in the center and 1 electron, then the hydrogen would have a neutral charge, but its valence band would be unhappy, and that's why hydrogen is very reactive. Okay. If we go down to the next row, we see over here lithium. Okay, if you've ever been in a chemistry class, you probably saw a video or a demonstration where they take pure lithium metal. Remember, it's a metal. If you take lithium and you dump that lithium into water, it reacts so violently it basically explodes. It's very, very dangerous. Lithium is so reactive. Well, why is that reactive? Let's look back here. Lithium had a number of 3. Okay. Right? Lithium is a atomic number of 3. It means it's got 3 protons. Okay, so that means that it'll have 2 electrons in that innermost valence band, but the next band, it wants to have 8, but it only has 1 more. If it has no electrical charge, it's got 1 electron in that second shell out there. And what that basically says is like, man, I'll just get rid of this electron. And so when it reacts with water, it's like, hey, you either take this electron or give me 7 more, okay? Because I want in this second shell, I want 8 electrons. And so it's very, very, very reactive. And you may have heard, like, of course, nowadays on cell phones and stuff, we use lithium ion batteries because it's a very light metal and it's very reactive. However, you may have heard years ago there were some issues with certain phones. They weren't allowed on airplanes because they've been known to just catch on fire because that lithium battery, if they don't merge it with the proper molecules, they're so reactive they could, literally catch on fire and cause damage. So and that all meets with this table of elements. It's just amazing how that works. Now, on the other hand, if you look at carbon, over here we see carbon is 6. Okay, the atomic number of carbon is 6. That means it's got 6 protons. So let's go back and look at this. So we've got the innermost shell has 2 of those, and then the next shell there wants 8, but we only have 4 electrons left. All right, so carbon is like half and half. It's got 4 electrons in that second valence band, but it would like to have 4 more. So carbon is what we call a semiconductor. It can't make up its mind. It's like I could either just dump these 4 electrons or grab 4 more. And I could kind of go either way, and that's why it's basically, carbon is a semiconductor. It's not a great conductor, okay, but it's also not a great insulator. It's just kind of right there in the middle. And so when we talk about resistors are made up, a lot of times they're made out of carbon material because it's got a lot of resistance in there. It's not a great conductor, okay, but it's not a great insulator. It's kind of in the middle. So most smaller resistors, the smaller size sort of things like this right here, resistor, I don't know if you guys can see that in the picture there or whatever, but Most of those resistors are made out of carbon because carbon is a resistive type material. We call it a semiconductor. It will conduct electricity, but it has a lot of opposition to that electricity. Okay? And if we look right below that, we see that silicon, we know, of course, silicon is kind of the famous semiconductor. It's got an atomic number of 14. So what does that mean? It means that the first band here is full with 2. The second band is full with 8, right? And then it's got 4 in that next energy band out there. And so it's got quite a few electrons, but it doesn't have as many as it would like. And so that kind of explains that. So when we talk about conductors, okay, remember the best conductor has 1 electron in its outer band. And if you look here, we actually have copper, which we already talked about, which has 29 protons. And so the first 3 bands are completely full, and you have this 1 electron out here all by itself, and so it makes a great conductor. Okay? Actually, better than copper for conducting is silver. Silver is actually the best, okay? And it's got that 1 lone electron out there. And then gold. Gold, both silver and gold are better conductors than copper, okay? Obviously, though, people like to use silver and gold for jewelry and other things. They're considered precious metals, and so that's part of the reason we don't use them for, copper wiring in our house or anything like that, because they're so expensive, because they're desired. But the other reason is, even though they're great conductors, they don't really make very good wire, okay? If you think about copper wire in your car or something like that, and you're driving down the road, copper is less brittle than silver or gold too. So it makes better wire. Even though it has a slightly higher resistance than gold or silver, it makes a better actual wire and sticks together and more flexible and things like that. And of course, it's not as heavy as gold. Okay, and we already kind of discussed here how voltage is a separation of charge. So if we can pull off those electrons and hold them over here and keep the electrons over here, and then we have a bunch of positively charged nucleus, or they're actually atoms because they do have the other electrons in them. We typically only strip off that 1 electron. And so we have all these other atoms over here, or molecules, that have, they're just missing 1 or 2 electrons, but they're a large molecule or atom, but they're positively charged. So we refer to those as ions. Okay, so they have a positive charge, but they're a large atom, or they're a large, a lot of times they're actually even molecules, which a molecule, of course, is made up of different types of atoms combined together. And they have a positive charge. So you have a positive charge and a negative charge, and then we have that force of attraction where the electrons want to get back and even out that charge. Okay, so that's force of attraction is our force. So the voltage is the separation of that charge, giving us the force that's going to allow the current to flow. And then the current is actually the flow of charge. So when we give them a path that those electrons can travel, right, that's that current. And so we talked about, like, carbon is a semiconductor. It's got that outermost band is only half full. So it's got 4 electrons in the outer band, and it would like 4 more. But copper is a good conductor because it only has 1 electron in there. So it's like, I could just get rid of this electron. I'll just pass it on and pick up another one later, kind of deal, right? Which is what current is, right? It's pushing those electrons away, but it's because there's other electrons coming behind it. And so copper is a great conductor. Carbon is not a great conductor, okay, but it will conduct electricity. And so we can pass those electrons through carbon, but we get more opposition to it than we do with copper. Now notice, copper is a good conductor. It's not a perfect conductor. What does that mean? It means that copper does have resistance. Gold does have resistance to electricity flow. Silver has resistance to anything will oppose, has some resistance, because I'm saying, if we're looking here at this copper and we see this electron down here, I'm saying we could push that off, but it takes some energy to push it off. And so basically that amount of energy it takes to push off is the amount of resistance. It doesn't, because it's being attracted by the protons. And so to just knock it off and make that electron move, we got to overcome that attraction of that proton. And that's going to take us energy to make it move. And so that means there's going, that's that opposition to leave, and that proton is the resistance. Okay, the fact that it doesn't want to leave that and be separated. All right, so now the amount of resistance in a circuit, or the amount of resistance is due to the type of material. Okay. So again, resistance is the operation to the flow of the electrons. Okay, and basically what resistance does is it takes that energy of that, when you get current flowing through something, okay, that resistance is basically going to take that energy and convert it. Okay, now there's something Newton talked about, which was the conservation of energy. Okay, you can neither create nor destroy energy, but what we can do with energy is transform it. So basically we have this electrical energy, right, this separation of charge, and these electrons want to get back to the protons to balance out that charge. But to do that, they're going to have to move through some type of material. And so the movement of those electrons is energy. And as they move through there, and when they hit that opposition, that resistance, that's how lights work. Lights are basically kind of resistors. And what they do is a light converts that electrical energy into light energy. Okay, so we take that electrical energy, which we really can't see, and we generate light energy. Okay, the most common form of resistance is basically heat. Okay, and you see this like with an electric space heater in your home, or maybe if you have an electric stove, you turn on that stove and electricity flows through that heating element. Well, that heating element is a resistor. What it's doing is converting the electrical energy into thermal energy. Now, any wire has resistance to it, which means that they will get hot. You're going to pass, if you're passing electricity through a wire, there's resistance in that wire and it's going to heat up. Okay. All right, so, but basically a resistor is going to convert electrical energy into thermal energy or heat. Okay, light will convert it into, like I say, light energy, a electrical motor, for instance, will convert that electrical energy into mechanical energy. So that's what a motor does. An electric motor converts the electrical energy into a mechanical rotational energy or work. All right. The unit for measurement is called the ohm. Okay. And again, this is named after a scientist. Okay. But we use, instead of using like a capital O, we actually use the Greek symbol omega for the unit of measurement. All right. Now, we can also talk about the inverse of resistance. So we say resistance is the opposition to current flow. Then we can talk about the conductance, which is the inverse of that, which means that if it's more conductive, then it allows electrons to flow easier. Okay. So conductance is the ability to allow electrons to flow, or it just means if it's very conductive, it has very little resistance. Okay. Conductance, they used to actually use the term mhos, which is like ohms spelled backwards, as the unit for that. But then they've come up with a new name, which is called Siemens. Okay, you may have heard of the German company Siemens. It's kind of like that, but it's actually named after a scientist again, so it's a capital S. So Siemens is the unit of conductance, okay, which is the reciprocal of the ohm. All right, so resistors will allow current to flow through them, okay, and they'll have different values. And so depending on what their value is, and depending on what your voltage is, will tell you basically how much current is going to be able to flow through there. Remember, the voltage is what's going to push the current through the resistance. Now, as that voltage pushes that through there, it's turning that electrical energy into heat. That resistance is converting it into heat energy, or if it's a light bulb, into light energy, whatever. All right, but what we use that term voltage drop because as it goes through that resistor, you know, let's say you have 100 volts and you're going to push it through two 5-ohm resistors. Well, basically what's going to happen then is you're going to, you've got two 5-ohm resistors connected in series. And so when you connect that up, the first one is basically going to drop 50 of those 100 volts. And then the second resistor is going to drop the other 50. So that when you get down to the bottom, you've got 0, would be your ground. Okay, but remember, you got to have a complete circuit for that current to flow. All right, so here's just kind of a picture of how we would build a fixed resistor. So you can kind of see here, here's a fixed resistor like this. It has two terminals. It doesn't matter when you connect this in the circuit, it doesn't matter which terminal you connect to which. Okay. But you can see they're made out of a metal or carbon film. So how do we do that? We basically use little strips of either some sort of metallic material, or if it's a carbon resistor, you know, we use a strip of carbon. So if we want to have more resistance, we have more laps around there. Okay. So actually the inside of these is a ceramic material. Ceramic is kind of glass as an insulator. So the current doesn't actually flow through that ceramic material. What is the purpose of that ceramic material? Well, it's got two purposes. One of them is it holds it all together, you know, for strength. And the other is remember, resistors are going to convert that electrical energy into heat. So it's going to warm up. And so the ceramic material is basically giving you a place for it to dissipate that heat also. All right, so if you're going to push more current through it, then you need a bigger resistor. So, and I know it might be kind of hard for you to see on the camera here or whatever, but let's see if I can find, here's like two different sized resistors here. There's a large one, a very large one, and then a smaller one. Let me see if I can get some white background there. I don't know if that helps you or not, but so the bigger it is, that means the more heat that you can make it hotter. You can push more electrical energy through it and make it hotter because it's bigger. It can dissipate that heat. If it's smaller, there's less heat that it can dissipate. Okay. Now these things could get hot to the point that if you put your finger on them, it could burn your, you could get a blister or something. You could get burnt on these. So the fixed resistors come in lots and lots of different sizes. You can have very, very big ones, and I have a separate video I'll be uploading that kind of shows a very large sized resistor, or very, very small ones that fit on a circuit board. And so, like I say, these especially these very large ones can handle a lot of electrical energy, and they can get very, very hot. All right, so here's like a precision power resistor. So this thing can get 25 watts. It's a 1 kilo ohm resistor, but it can handle 25 watts. Watts is kind of a measure of power. Power is instantaneous work. Okay, so remember, work is force times distance. What power is like force times distance, but in an also a measurement of time. How quickly did you move it? Okay, so like if you say, oh, well, here's this item, and I'm going to move it from here to here, but if I'm going to take an hour to move it that distance, that's not really all that much power. But if I move it in a split second, and I move it really fast, all right, that takes more power to make it move faster. And so power is basically work in a short amount of time, or it's the measure of that instantaneous amount of work. All right, so when we're going to be drawing electrical circuits, when we draw these circuits, we use one of these two symbols usually to indicate a resistor. Usually it's this angled kind of thing showing that if you think about it, there's electrons flowing through here. They're going to like be getting their head banged around as they bounce up and down through this zigzag thing. So that's kind of the idea. It's like, okay, well, the electron's moving through there, but he's got to go up and down and bounce all around to get through it, and that's that resistance term. But sometimes we just draw it a little simpler and just draw like a rectangular box to indicate that there's something in there that is going to oppose current flow. Here's a picture of a circuit board, and it just kind of showing you the R's, R1, R2, R3 are resistors. I'll just kind of go over this other stuff. We won't really discuss too much in this class, but the C1 over here to the right is a capacitor. The Q1s at the top are actually, the Qs there are representing transistors. The IC1 is an integrated circuit, right? So that's a chip. And the Ds, D1, D2, D3, whatever, those are diodes. Okay. So just kind of let you know what those different things are. All right, we also have variable resistors. Variable resistors are usually potentiometers, and a potentiometer will have 3 terminals on it. So you have here, this is a fairly large power potentiometer, and it has 3 terminals. If you just go to the 2 outer terminals, the resistance doesn't change, so it's actually a fixed resistance between those terminals. But this center terminal has a wiper blade. I don't know if you can see that in the camera there, but there's a wiper blade, and when you crank the knob, that wiper blade will spin around and give you a variable resistance between that center terminal and the other 2. Now, they also have what they call rheostats. Rheostats basically just has 2 terminals. Most of the time, anything you go buy that's going to be variable will be a potentiometer, but you might connect it as a rheostat where you don't use one of the outer terminals. You just use one outer terminal and the center terminal to make it variable. All right, so here's kind of a picture. I mean, there's several different pictures of these. Again, these come as power, very large resistors that can handle a lot of heat, to very small ones that fit on a circuit board, can be soldered onto a circuit board. And then there's little screw terminals there that we can adjust those. So here's a couple of different symbols showing potentiometers, trying to illustrate that it's a variable resistance. All right, so when we have these resistors, if it's a big resistor, then it'll have stamped on it how much resistance and how much power it's rated for. But a lot of these resistors are so small that they can't put the information in there as text where we could actually read it because they're just too small. So what they've come up with is something called color code, and they just put these stripes on here, and each color of stripe gives you each color of the stripe here tells you a number, and then based on that we can then determine information about this resistor. So in this case, the example here I have, there's 4 stripes. Now notice the stripe number 1, the red stripe is labeled number 1 there, is closest to the edge. And so that's how you kind of can tell which side of the resistor you look at to figure out which stripe is number 1. It's going to be the stripe closest to the metal terminal. And like number 4 here has a much more distance away from the other metal terminal coming out of the resistor. All right, and so here you can see we have a red, and then we have a black, and then we have a brown, and then a yellow. So there's 4 bands, color bands on this resistor. And so what you do when you look at this, the first 2 bands basically give you a numeric value. The 3rd band is called a multiplier. And then the 4th band is a tolerance. Okay, when we build these things, we can't always be 100% precise. Yes, this is that resistance. And so the 4th band tells us how accurate these are. All right, so let's just kind of take a look here. First thing we got to do is we got to match colors to a numeric value. So the colors are black, brown, red, orange, yellow, green, blue, violet, gray, and white. Okay, so those are the choices of colors that they use for the first 3 bands. Okay. And so it's 0 is for black, 1 is brown, 2 is red, 3 is orange, and so on. You can see that on that chart there. So when you look at this first resistor I had, 1 was a 2, and black was a 0, so that's 2, 0, and then brown is a multiplier. Okay, so you have a 2 and a 0, and then you have 3 was 3 is brown, which is a 1, but that's 10 to the first power. So let me come over to my paint here for a minute. All right, so we have red, which was a 2, and then we had black, which was a 0, and then we had brown, which is a multiplier. Brown is a 1, but what that means is 10 to the first power, or 10. And so therefore, the resistance then is 2, 0, and then times 10, okay, which gives us 200. So that's 200 ohms. Okay. So that resistance is of this resistor right here is 200 ohms. So it's 200 ohms. And so if we wanted to put this into Blackboard, okay, technically we might want to put in the omega symbol, but putting in the omega symbol on Blackboard is kind of difficult. So I will take it, but we need 3 significant digits. So remember, when you're doing 3 significant digits, you need to put in a period there. So the correct answer in Blackboard for this would be 200 period. That period is required, and then ohms. All right, now these color codes here, black, brown, red, orange, memorizing that can kind of be difficult. So to help with that, people have come up with mnemonics, right? The idea of a mnemonic is to help you remember something. And so here's just a couple of mnemonics that I've found over the years. Actually, I just learned one of these. I recommend you just pick one and learn it. Okay. The down here at the bottom is a wiki link. Okay. And so if you click on this, they give you lots and lots of different ones. But like I say, just read through them, find one that works for you that you can remember, and then just remember it, and that's it. Okay. So we have here I just put a couple of them on here for you to try to remember. But if you don't like either of the 2 I have there, you can go to the wiki links and pick one of these other ones that help you remember those. Okay. So you just you really need to do that, so that when you're working with these resistors, you can look at the color code and make sure that, hey, that is this color, or that color tells me this is a 100 ohm or 1000 ohm or 5600 ohm or whatever. Okay. All right, and so there will be a lot of quiz questions and things about using these color codes. Okay, so you need to learn the color codes. Now, when you buy these fixed resistors, you can't go out and buy a fixed resistor of 233 ohms. Okay, they come in these standard resistance values. So if you look here, this is a little table that shows you the most common values that you can find. So if you wanted a 1000 ohm resistor, no problem. Okay, you can go out and you can buy a 1,000 ohm fixed resistor, something like this, and they're readily available. 10,000 ohms, 100,000 ohms, or even a million ohm resistor. We'll use that in lab next week, a 1 mega ohm resistor, 1 million ohms. Okay. But as we kind of go through, you see like you can also buy 2,000 ohm resistors. They're actually less common though. Usually the most common in the 2,000 range you see is like 2.2. Okay, so you can buy like a 1.0 K 1,000 ohm. 1.2 is pretty common. 1.6, 1.8. They do make the 1.3 and 1.5 like it shows here, but those are much less common. And then they go to like 2.2, and then 3.3, and 3.6, 3.9 are pretty common. 4.3, you can get them, but they're not that common. 4.7 is extremely common, or 5.6 is extremely common. So you see, like if you wanted a, let's say you wanted a 4,500 or 4.5 kilo resistor. Well, you know, you could buy like a 4.3, and then you would need a 200 ohm, and put those in series, and that would give you the amount of resistance that you need. Okay. But we also have to worry about the tolerance. Okay, I mentioned that fourth band is the tolerance. The tolerance is how much it can vary. So if you look back here, like on this slide, down at the bottom we have silver and gold. Right? The colors silver and gold, you usually only see those on the fourth band of a 4-band resistor. You may actually also see them as the multiplier, which actually makes it a fractional multiplication, which you can see in the book, they talk about it. But when we talk about tolerance, a silver band would be 10% tolerant. Gold band would indicate 5% tolerance, and a red band would indicate 2% tolerance. All right, so if I had a resistor, and just pick some easy numbers here. Let's say that I had a resistor that was brown, black, brown, with a red, or no, let's do a silver first, with a silver. Okay, then that means that this resistor would be 100 ohms plus or minus 10%, which means that this resistor could vary between 90 to 110 ohms. On the other hand, if I had a resistor that was brown, black, brown, but had a gold band, then that's 100 ohms plus or minus 5%, which means that this resistor is only allowed to vary between 95 to 105 ohms. If I had a resistor that was brown, black, brown, with a red band, it would be 100 ohms plus or minus 2%, which means that this resistor would only be able to vary between 98 to 102 ohms. If this resistor here, if you bought a bunch of these resistors and then you started measuring them, and one of them measured 103 ohms, it would be out of tolerance. Okay, So this resistor that measures 103 ohms, but had these colors as the bands, would be out of tolerance. So we would consider that a bad resistor. All right. And so, ideally, you wouldn't be able to buy one like that. But sometimes if you overheat a resistor, if you put too much current through it and make it hotter than it was supposed to get, then you're damaging that resistor, and therefore it may no longer be the resistance value that it's rated at. So you always need to make sure that you don't put more current through a resistor than it's rated to handle. And we'll talk about power later on. I think that was chapter 4. Right now, officially, we're in chapter 3. Okay, but I guess we do have it here in these slides. So resistors have two rating values with them. They have the resistance value, which is ohms. The unit is ohms. But they also have that power rating, like I said, because you can't overheat that resistor or you damage it. Okay, so it's only designed to have so much current flow through it, and that is gives us the wattage rating, and we'll talk about that. Watts are actually measured by current times voltage. All right, so to measure these electrical properties we've talked about voltage, we've talked about current, and we've talked about resistance. We can get something called a multimeter, and that multimeter can measure all three of these. Okay, it can measure voltage, it can measure resistance, which they refer to as an ohm meter, and it can measure the current. Okay, and so you can get these. The older style were what we called analog meters. Sometimes the analog meters, usually they were referred to as a VOM, which is a volt ohm milliamp meters, because they might be able to read amps, but usually reading milliamps with a meter like this. If you want to measure very large currents, they actually make special meters for them. If you're trying to measure like 100 amps, you can't do that with these meters. You would destroy either one of these meters if you tried to put 100 amps through them. Actually, when you try to measure current, they have fuses in them so that the fuse will blow to protect the meter. So hopefully, if you tried to shove 100 amps through it, the fuse would blow before it got anywhere near that, and it wouldn't damage anything but the fuse, and you could just replace the fuse. Okay, but the analog meters are usually referred to as a VOM, volt ohm milliamp meter, and digital meters are usually referred to as DMM, which is just digital multimeter. Most of the time with a DMM, you're going to be able to read voltage, resistance, and current, and you may also be able to measure the HFE of a transistor. You may be able to measure capacitance with some of the more expensive ones, but the most common thing is to measure voltage, resistance, and current. Okay. Some of the cheaper ones maybe only will measure voltage, and they still call it a DMM, but most of the time, DMM means multimeter, which means you can measure more than voltage. All right, when we measure voltage, you need to connect the meter in parallel. So you take your voltmeter and you put the two meter wires. You have a positive meter wire and a negative meter wire, and you have to put them across the element you're trying to measure the voltage drop of. If you connect the voltmeter in series, what will happen is the voltmeters have a very, very large resistance. So if you interrupted the circuit and tried to inject the voltmeter in series, it's got this really, really large resistance, which is going to oppose any current flow, and you basically get nothing. Okay. On the other hand, a current meter, when you measure a current meter, you need to measure that in series, unless it's a special one. The one shown on the right is called an inductive meter, and you don't actually have to break the circuit to measure it. But these meters here, you actually have to interrupt the circuit and wire it in series. So we're going to be doing this in class, so please pay attention here. You notice there's multiple terminals here. You see this on the DMM over here, there's a red one that has like a V and a omega there. That's for measuring either voltage and resistance. Over here, there's little red boxes and it says A over there. That's for measuring current. So if you're going to measure current with a multimeter, you have to physically wire into the meter into different terminals. Okay? And the reason for that is because voltmeters are measuring voltage in parallel, but current meters are measuring it through in series, and so they have a very small resistance. If you plug into these terminals with the A on it, you can blow a fuse. Okay? If you blow a fuse, obviously it's going to cost you some money, because you have to replace that. In this class, we're not going to charge you for that fuse with money, but I will dock points if you blow a fuse. So I give you the first fuse free because maybe it was blown when you picked up the meter. Somebody put it back without reporting that they blew it. But if you blow a second fuse, it's 2 points. If you blow a third fuse, it's 5 points. If you blow a fourth one, it's 20 points. Okay, so you need to be very careful when you're trying to measure currents and voltages that you're hooking the meter up correctly. And you physically have to rewire the connection into the meter to measure either a voltage or a current. All right, and I'll do a video on that later, and we'll discuss that when we're actually in the classroom. To measure a resistance, you need to make sure there's no power applied to the circuit, and you need to disconnect the circuit from the power supply. Okay, so when you're measuring resistance, you just basically take the meter and put it across the thing that you're trying to measure. So if you want to measure the amount of resistance, which you need to do for every lab, you'll be getting resistors out, and you need to measure the resistance and use the measured values. All right. You can also use an ohm meter to determine like whether a piece of wire is good or not. Remember that all conductors have resistance, but it's a very small resistance. So if you take a piece of wire and you put the meter in ohm mode to measure resistance, and it has a very small, almost zero resistance, then that tells you that it's a good wire. But if there's a break in the center of the wire, then that would be considered an open circuit or an open wire, because there's a break in it, current can't flow. All right, so that thing here. So if we had let me move over here, I guess. Okay, so let's say that I had brown, which is 1, black, which is 0, and then the multiplier was red. Okay, and then the fourth band was gold, which is 5%. Okay, so what that would say is we have a 1, 0 times, oops, I'm sorry, that red was incorrect. Red was 2, sorry about that. So we would have 1, 0 times 10 to the second power, right? So that would be 1, 0 times 0, 0. So a brown, black, red for the first three color bands is a 1,000 ohm, which would be 1.00 kilo ohm resistor. And the tolerance of that would be 5%. So 5% of that would mean that this resistor could vary between 950 ohms to 1,050 ohms. Now, if we do gold as a multiplier, let me double check here. You don't see it very often because gold is a very small. Gold and silver as a multiplier is a fractional multiplier. So let me just double check here. I forget whether silver is 0.1. One of them's 0.1 and one of them's 0.01, but I see them so seldom, I don't even remember. Yeah, we're not looking at rings. Okay, gold is 0.1, silver is 0.01. I couldn't remember because, like I say, you don't see them actually all that often. So for the gold as a multiplier, okay, so let's say we had brown, black, gold is 0.1, okay, which is actually 10 to the minus 1 power, right? And then say it was red was your 2% tolerance band, okay? So this resistor would be 1, 0 times 0.1, which would be 1.00 ohms. And the tolerance is 2%, so this resistor would be allowed to vary between 9.98 ohms to 1.02 ohms would be the variance of this resistor. Okay, so does that show you the difference? This is the third one is the multiplier. So if red is the multiplier, you take the first two numbers and then you basically multiply them by that many zeros. Okay, so you got 2, red is 2, so then you basically tack on 2 more zeros. But if gold is the multiplier band, then you're actually doing a fraction of that. You're actually dividing by 10. So you had 1 0, which was 10, and we multiply times 0.1, which gives us 1.0. And then the tolerance of that was red.